Hello, everyone, and welcome to our third lecture of CSC 110. And in this lecture, we're going to start moving in a different direction. In the previous lecture, we went over technological revolutions, and I'm going to review a little bit of that. And then we're going to look at some another history, and that is the history of representing numbers. Okay. Now, I should say something about the course in general. We start pretty abstract. Okay, so if this lecture feels like it's a little bit much, don't worry, it's not really characteristic of the rest of the course. The reason I want to do this is because I want you to understand the essence of what computers are. And so, we went through this technological thing to history to describe how technology affects us, and now I'm going to start focusing more on the history of like how we got computers, and the purpose is to really have an understanding of the essence of computers. Okay, so let's start. So first, the summary of technological revolution. So I'm not going to repeat everything I did then, but in the last lecture, but we went through these different periods as humans, and at some point in our history, a new technology entered our society and it changed us. So, what are some of the properties? That's why we looked at that history. What are some of the properties of what can we say about these technological revolutions? And the reason we want to think about them is because we really can't predict the future, but we can say some things about it. And so, by looking at our past and seeing how these technologies affected our past, we might be saying something about how it's affecting us today, how computer technologies affect us today. Okay, so I just made some points, and these are sort of like overarching themes that we learned our history. The first point is that technology is transparent. Okay, and what I mean by that is that you don't always know that you're using technology. You don't think to yourself, when you're using your fork or knife, when you're eating, you don't think to yourself, oh, this metal came from the Industrial Revolution, and it was made by, and from the Iron Age, and it was made by all these things. And you don't think of that. You don't even think that you're holding a fork or a knife. All you're doing is you're just cutting your food, okay? And you're thinking about eating. That's where the focus of the attention is. And the tools, they're just the means by which you achieve that goal, and you don't think of them, okay? And the example I gave was a doorknob, but you can go through all your examples, when you're talking to someone on the phone, because your phone is a tool, you're talking to someone on the phone, and what's going on? I mean, you're talking, you're thinking about, making plans or whatever. The phone disappears, all the functioning of the phone, all of those things disappear. Okay, so that's what I mean by technology is transparent. The other thing is that when a new technology arises, it transforms our civilization. Okay, not every discovery is a new technology. Not all discoveries are even technology. As we'll see, there's some mathematical discoveries about numbers, which we'll talk about in this class. But when some discovery of some new technology arises and it catches on, it fills our society, it fills our world, our civilization, and there's really no going back. Okay, there's no going back. Now, you should be aware that not every technological discovery is good. It brings good with it, but also brings bad with it. And so it's always this kind of forward ratcheting thing. And it's, if we bring a new technology into our world that brings a lot of bad with it, it's going to be very difficult to get rid of it. Okay. And unfortunately, I mean, I don't know if we have that much control. Okay. So I've got some examples here. From hunter-gatherer to agriculture, that was good because we had this new food source available. We had control over our food source, okay? Whereas during the hunter-gatherer, we had to chase our food. We really couldn't control it, but now we can plant our food, and we have much more control over it, okay? And that's what the agricultural revolution, that was the good. And here I have the bad, warfare, okay? And I think I spelled that wrong. Warfare and disease. Okay, warfare because people would just steal food from one another. If you had a marauding group of humans, they would come and they would just steal the food from some village. Or disease because you would live with your animals, and then there'd be diseases in the animals that would jump to humans. Okay, in the Industrial Revolution, we had mass unemployment and poverty because machines were displacing people from their jobs. Okay, some of that is happening even today with the information age. Okay, and another technology is more recent is nuclear technology. Okay, I think I would put that in with the end of the industrial revolution, and like atomic bombs and thermonuclear warheads, they're not going to go away. So we live in this continuous threat that we could blow ourselves up, and the only thing that's stopping us is our own holding back from that kind of insanity. Okay, so there we go. All right, and the next point is that I think I did already say that. Okay, not only does it transform our civilization, but there's no going back. Okay, and here I can give you some examples. Cars are a product of the Industrial Revolution. They displaced like horse and carriage. And could you imagine living without a car today? It'd be pretty hard. You go to get a job, and they say to you, you have to be here in such and such a time. You go, well, it's going to take me a lot longer to get from home because I'm walking. And they go, walking? Why? And so why live without a car? And yeah, it causes difficulties that way. Okay, it can be done though. It can be done. There are other accommodations, and we make other accommodations available to people. But generally speaking, it is it is something that our society simply can't do without. Okay, actually, I could mention like ideas of climate change. When people say, how do we deal with all these fossil fuels that we're burning, people say, well, they're not saying get rid of the cars. What are they saying? They're saying, well, maybe we can consolidate the cars by carpooling or using public transportation. Maybe we can move to cleaner technology, but they never say let's get rid of the cars, okay, and let's start walking. So I think you got the idea. And then phones as well. Okay, those are the major themes that we get by just looking at how technology has affected us in the past. And we might say, oh, well, that's what's going to happen into the future. Okay, and there's unfortunately no going back with computers. They're in our lives right now. Okay, but it's good to have this awareness. All right, so that's enough of a summary. What are we going to do today? We're going to talk about number systems, okay? And that is how numbers are represented with symbols. And we're still not at computers yet. And just some of the technological discoveries that I talked about last time up into the Industrial Revolution, those were important for computers, but they're not sufficient to make computers. In other words, you have to have, like in the Industrial Revolution, the ability to replicate. Okay, later on I'll show you how computer chips are made, and very briefly, okay, using silicon wafers. And that requires this idea of replication, which came out of the Industrial Revolution. All right, but if you just had the idea of replication, that's not enough to make computers, or at least not enough to make the kind of computers we have today. All right, so to get the computers that we have today and the computer technology that we have today, we needed to think about numbers in a different way. And so today, or in this lecture, I'm going to trace out that particular history. Okay, and so let me start off by saying, what do I mean by representing numbers? And I mean, like representing, like counting. Basically, I mean counting. Okay, so here I say representing whole numbers like 1, 2, 3, 4, 5. There are different ways of doing it, different ways of thinking about it in your head, and different ways of writing it. Okay, and that's what we're going to study. And I'm actually going to show you how to represent numbers using ones and zeros, and this is known as binary. Like that, okay, the binary number. So that's where we're going to get to by the end of this lecture. Okay, at this point you're going to say, wait a minute, I mean, my major is not computers or any kind of maybe like mathematics or any hard science or anything like that. Why are you going to teach me about binary numbers? Okay, like why are we going there? And there's some good reasons. Okay, I guess reason number 0 that I didn't even write down here is that every introduction to computer course teaches it. Okay, but they teach it for a good reason. So let's go over those reasons. Okay, so the first reason is that we really want to get at the essence of what computer technology is. So we call it the information age. Probably the better name for it is the digital age. And even better would be the binary age, but no one calls it that. And this is a very deep thing that this new technology brings. Okay, it's the idea that you can take all information, human information and basically distill it down to ones and zeros. So if you really want to understand the essence of computer technology, you really do have to understand how things can be represented in terms of ones and zeros. I say things, I mean information, and I'm going to do some information, but in this particular lecture, I'm just going to look at how numbers, like whole numbers, are represented in terms of ones and zeros. Okay, so that's one reason, and the next thing is related. These are all related. They're not independent reasons. The next reason is I want to show you how you can build a mechanical mind. Okay, now this almost like impinges on philosophy. It's a little bit unnerving, you know, to think about humans and machines this way. Well, what do I even mean by a mechanical mind? Well, a mechanical muscle is a machine which does things that the human body could do with its muscles. Okay, like the bellow, a perfect example, is a human lung. And you say, well, is that a muscle? Yeah, well, the diaphragm is what, you know, the muscle that pushes air in and out. And that allows us to blow, okay? But the bellows externalizes that function into a machine, which is able to blow air and make fire hotter, okay? And so that's an example of a mechanical muscle. There are others, you know, like the loom is another kind of mechanical muscle, okay? And so on, all right? It takes the place of us physically having to weave one string between a whole bunch of other strings, okay? Which you can do, okay? I guess that's, I don't know if that's called knitting or crochet, but you know, you understand the idea. Okay, so now what I'm saying is that just like we externalized our lungs into the bellows, we can externalize our minds and make a machine that functions the way our mind does, okay? And so in learning about how a computer works at its deepest level, we're kind of learning something about what human cognition is, okay? I don't think it is that this is at all complete, but it's good to see this, okay? It's good to see this because it gives again an understanding of technology and digital technology in a way that you wouldn't understand otherwise if you didn't think about it this way. And so a little bit of a spoiler alert: all the functioning pieces inside a computer, they're not moving pieces, but they're functioning pieces. They are all at the deepest level, very, very tiny switches, like on and off switches, like, you know, for a light bulb. Okay, they're switches, and switches can be in one of two positions. Now I know there are variable switches, you know, where you can like dimmer switches and things like that, but I'm just talking about regular plain old lights on, lights off switches. Now on and off are two different states. You know, the switch is either on or off, and that corresponds to the ones and zeros of binary. You can think of one as like on and zero as like off. Okay, and so that's why we're gonna head in this direction, okay? And actually, I'm not gonna, you know, again, this is not a course in computer engineering, but at some point, I'm actually gonna design for you a machine made out of switches which adds. So I'm actually gonna design for you an adding machine. Now it's not going to be a physical adding machine, although I could make a physical adding machine this way. It's actually going to be in terms of a computer program that is used by electronics engineers to design computer circuitry. Okay, and but the point is to understand it, and you'll be amazed. I mean, this sounds overwhelming right now. I hope it isn't, but you'll be amazed. You'll say, yeah, you know, I get it. You can really build an adding machine. And what's really good about this, like, I'm not doing it just for no reason at all. The reason I'm doing this is because you can then see how you could build this mechanical mind, and you could take these things which are not really intelligent in and of themselves. A switch, like, you wouldn't think of a switch as having any kind of intelligence. But as I start adding up switches and switches and switches and switches and switches and switches, and I get a whole bunch of switches that are all interconnected with one another, suddenly this intelligence emerges. And the intelligence that emerges is adding, the intelligence of adding. Okay, and so really I think the point of building this adding machine is to show you how the cognitive function of adding, something that our human brains can do, can be externalized into a machine. Okay, and it does even say something about our own brains, because our brains are made out of neurons. Now, neurons are not switches. They're much more complicated and stranger things than that. But you know, one neuron by itself you can't say is really intelligent. Okay, two neurons are not intelligent. But as you start adding neurons to neurons to neurons to neurons to neurons, you emerge. Your consciousness emerges. Okay, so this is kind of freaky, isn't it? So that's another reason to do this. All right, now it's not quite as magical as what I just made it out to be. By the time you see how this adding machine works in terms of switches, you're going to go, meh, okay, I get it, and so what? But from this perspective, it's kind of magical, isn't it? It feels like this is magic, just like you feel like your phone is magic. It's not. It's a machine. And so once we get rid of the magic, we have an appreciation of the essence of what computer technology is. Okay. And the last point, I think I kind of made it already, but it's worth repeating again in more detail. And that is that accompanying this externalization of the human mind as a mechanical machine, okay, is also the externalization of information. Information today has been digitized. And so by the end of this lecture, hopefully you'll see that, representing whole numbers, counting numbers, you can also call them counting numbers, like 1, 2, 3, 4, 5, not 1.5, no fractions, no, not negative numbers, not even zero, okay, although we'll have zero in there. But when you count things, you count 1, 2, 3, 4, 5. You can represent counting numbers in terms of just a string of 1 and zeros, like a sequence of 1 and zeros, okay? And you go, okay, well, so what? Well, here's the thing. Not only can you represent numbers, okay, as a sequence of ones and zeros, but you can then, and I'll show you this in a later lecture, you can also represent the English alphabet, okay, as a sequence of 1 and zeros, okay? And then not just the English alphabet, all alphabets. Okay, the English alphabet first, because it doesn't have all those kind of like accent marks and things like that. Like Spanish on top of the M has the tilde for like ño, okay, like in señor, okay, and things like that. Okay, so other alphabets have more complications. They can be represented as a sequence of ones and zeros. Okay, then it gets more interesting. Even colors can be represented as a sequence of ones and zeros. Okay, and we'll learn something about how human information, like how we understand the world in terms of colors, and then how we digitize that. Okay, so not only am I showing you that it can be done, I'm giving you an appreciation for like how colors can be a sequence of ones and zeros. And at this point, this should sound like magic. You look at this color red, and there are different shades of red. You look at a particular shade of red, and I can distinguish that one shade of red from another shade of red by its sequence of ones and zeros. Okay, so we'll see how that works. And then, of course, once you can do colors, you can do entire pictures. Okay, can be represented in binary. All right, and video can be represented in binary. And audio, I don't think I put that down there. I did. Audio can be represented as binary, and like all human information can be represented as binaries. And so you can have libraries, and not just like regular libraries with books, but digital libraries, like an entire compendia, like of entire accumulations of human knowledge, as a kind of a library where you can go in there and look up stuff and stuff beyond what the human mind can hold. Okay, so that's why we're doing this. Okay, and let's see here. I had another point. Oh yes, the last point is not only will, and this is follows on the previous point, not only will you understand how information can be digitized as a sequence of ones and zeros, but I'm also going to show you how you can measure how much information is in a particular piece of, I don't know, literature, art, video, whatever. Okay, and this, now it's getting practical. Okay, now it's getting very practical, because when you go out and you get like that USB stick, and you look on the side of the USB stick, if you have one right now, you can look at it. Okay, and it says something like 64 gigabytes. Okay, that's a little small these days, but you can still buy 64 gigabytes, 128 gigabytes. Okay, or 256 gigabytes. You go, what is that? What does that 64 gigabytes mean? Okay, what is a gigabyte? It's a measure of information. So that's interesting, because what that means is that we can measure information. Now, just to tie to maybe some other classes you have, especially if you've had a physics class, there's only 3 fundamental things that you can measure, okay, at least in physics. One of them is length, how long something is. And what do you use to measure length? Well, a ruler, okay. The other one is time, which you can measure with a clock. And another one is mass. That's how much stuff is present, okay? And that you measure with like a balance, all right? And I'm claiming now there's a fourth. You can actually measure information, Okay, and there's an equivalent of this in physics and chemistry. It's called entropy there. Okay, but I don't want to go too far afield. Okay, I just mentioned this in passing. All right, and you might say, well, there's a lot more things that I can measure than just length. No, those are the fundamental things you can measure. So like temperature, you think about how you measure temperature with a thermometer. On the side of the thermometer, there's a ruler. So you're measuring the length of the column of mercury or alcohol or whatever against against the ruler. And so, it's all, in other words, um, all these measurements can be reduced down to these four fundamental measurements, one of them being information. Okay, so and we're only going to study information in this class because it's computers. I just wanted to mention the other ones, because they're part of it. Okay, so I've kind of given you an overview of where we're going with all of this, because I didn't want to just jump into numbers and you're going, well, why are you teaching me this? So that's why I did this. Okay, so let's start off. And here I call this very early numerals. Okay, and numerals because it's like the how we write down the numbers. Okay, I mean, humans have been counting for a long time verbally, but like, how do we write them down? Okay, well, one technique is to just put a stick, like a line, for every item that's out there. Okay, so you might have, like, I don't know, three animals, three cows. Okay, they might all look different than one another. Okay, one might be brown, one might be black and white, and I don't know, the other one's just black, say. Okay, and the colors don't matter. One might be bigger, the other one might be smaller, and so on. The sizes don't matter. We just want to abstract out how many of them there are. And so we say there are three. And you say, well, how do I represent three? Three cows, three sticks. Okay, something like that. All right. And you can count this way. Okay, so again, when you think of counting, think of like 1, 2, 3, 4, 5, and so on. Okay, so we're over here. Okay, so you have 1. And then you have 2, then you have 3, then you have 4, then you have 5, okay, then you have 6, then you have 7, and you start to see a problem happening here, okay? And the problem is it gets harder to read the number the more sticks there are. And so if you take a look at 6 and 7 here like this, okay, now they're side by side, and you know that 7 is on your right and 6 is on your left, but you're going, well, if I just saw those sticks there, I wouldn't be able to look at the sticks and go, oh, that's the number 7 or that's the number 6, because they're kind of close, okay? And maybe you could do it with 6 and 7, but then 7 and 8 gets harder, 8 and 9 gets even harder, 9 and 10 gets even harder, and so on and so forth. So if you try to count up to infinity this way, you would stop pretty soon, okay? As soon as you had, like, I don't know, 125 of something, you go, okay, that's it. I'm not drawing 125 sticks. And it would be useful to whoever you're showing it to anyhow, okay? So it's useless, not useless, but it's hard to count. It's easy to add, okay? Because if you have 2 sticks and you add 3 sticks to them, you have 5 sticks, and you just like literally put the lines together, okay? It's kind of easy to multiply, all right? Because this says you have 3 bundles of 2. And so for each of these sticks, you make a bundle of 2. So my first stick, I have a bundle of 2. My second stick here, I have a bundle of 2. My third stick, I have another bundle of 2. Okay? And so a bundle of 2 plus another bundle of 2 plus another bundle of 2 gives you a bundle of 6. And so, it's not that bad to multiply. You can do that too, okay? But there are some writing systems that use this, like, early on. I think the very earliest Sumerian way of writing did do this, but I mean, it stops pretty much at 5, 6, or 7. Okay, and you don't go any further. Okay, and writing was originally used as contracts, when you were exchanging stuff. Okay, stuff like that. Okay, all right. So what's next? Well, the next are Roman numerals. Okay, how did Roman numerals work? So Roman numerals basically were the number system that were used by the Romans. And the Romans, they were Iron Age, okay? So I don't know if you've studied the Romans in your other classes, But and here I'm concentrating on Europe because I need to follow that history to computers. Okay, so the Romans they pretty much ruled all of Europe. Actually, just really, I should say probably the Mediterranean basin. Okay, and that's all the land around the Mediterranean Sea. And they had a number system, and we inherit it today. Okay, we use it. Okay, and so how do Roman numerals work? Well, they start off using the stick system, 1, 2, 3. But then by the time you get to like 5, it starts to get annoying. And so 5 is a special symbol. It's the symbol V. All right? V for 5. Why? I don't know. It's not even like the Latin word for 5 is quinque. I don't know how you get a V out of that. But okay, so 5 is V. And now 4, you could do maybe as 4 sticks, but there's another way to do it. And that is you say 1 before 5. Okay, and so the way the Romans thought about this is like 1, 2, 3, 1 before 5, 5. And then 6 was 1 after 5, 2 after 5 was 7, 3 after 5 was 8, 1 before 10, X is 10 right here, and 1 before 10 is 9, and then 10 like that. Okay, so they counted, a little bit using the stick method, but then they anticipated what was coming next. Okay, now why? What problem did this solve? This solved the problem of big numbers. Okay, and so this is counting to 10. Then when you got to 11, you would do xi, which would be 10, and then 1 after 10, which is 11, and then you would do 2 after 10, and maybe I should just finish this off. Okay, then you would do 3 after 10, then you would do 1 before 15. And so maybe I should just show you 15. 15 would be 5 after 10, which is 15, and this would be 1, whoops, I got it backwards. 1 before 5 before 10, like that. Oh, sorry. There it is. Okay. Okay, I haven't used Roman numerals myself in a long time. Okay, so this would be 10, and this would be 4 after 10, and 4 is 1 before 5, and then you get 15, and then you get 16. Okay, and then you get 17, and so on. Okay, like that. All right, I'll just put some dots there like that. Okay, and then you had 20. You know what? I didn't put 20. Let me go up to 20. So then you have here's 18, here's 19, and here's 20. So 20 is 2 10s. All right, and then you would have 21, 22, and so on, and then you'd have 31. So 31 is 3 x's, that's 30, each x is 30, and then 1 after that is 31. And then when you get to 40, 40 is just that part that I've got highlighted. It's 10 before 50. 40 is 10 before 50. 50 is an L. Maybe I should just write that down. I don't know. Here, I'll go right to the end here. 50 is L. All right, so you'd have like 41, 42, 43, 49, and then you get up to 50 here like that. Okay, you get up to 50, and so 40 is 10 before 5. Okay, it's good enough. I'm not going to test you on Roman numerals. I just wanted to remind you about how those number systems work. Okay, and what problem did this solve? Like, why do this? Well, because then you get rid of the too many sticks problem. Okay, so that as you start to count up to 50, you could just represent 50 with one letter, L. All right, why the letter L for 50? I don't know, but just L for the letter 50, the letter L for 50, and that saved you from having to write 50 sticks. Okay, but it's kind of a kooky way of counting. All right, and that's why I call it a messy system. All right, it's okay if you want to put a big number in just a small number of symbols on, say, a building. So you go to buildings, and buildings always have the year that they were built in Roman numerals because it's kind of, I don't know, antiquated, it's quaint, and so it looks nice. And that's what we use Roman numerals for today, just for something ornate. Okay, but try adding with Roman numerals. So up here I had 2 plus 3, and that was easy to add because if you had 2 sticks and you added 3 more sticks, you have 5 sticks. But now look at the magic that happens here. You've got 2 sticks, then you add 3 more sticks, and somehow the 5 sticks together magically turn into a V. And you say, well, okay, I can just memorize that. Yeah, but it starts to get worse and worse and worse as you add bigger and bigger numbers. So if you're adding like 365 to 739, that gets pretty messy to do that. It gets pretty messy to do that. Multiplication is even worse. I don't even know, I can't even imagine how they did multiplication with Roman numerals. But if you have 3 times 2, it isn't just a matter of 3 bundles of 2 sticks per bundle, okay, which adds up to 6. Somehow magically, 3 sticks multiplied by 2 sticks gives you a V followed by an I. And this is not at all easy, okay? They probably had a lot of intermediate steps. I should probably look up, it's not part of the course, but just for my own edification, I should probably look up how the Romans actually did do these things, because they must have had some rules. But whatever those rules are ugly. Okay, they're not at all intuitive. And here's the point. Why are we doing this? Why are we studying this? Because we want to build a mechanical machine that does this. And it would be really difficult to build a mechanical machine that adds in Roman numerals. Okay, so if you want to learn more about Roman numerals, that's enough for the course. Okay, but if you want to learn more about Roman numerals, the wiki page is really good. I'll show you wiki pages that are good when they are. And here's the nice thing, like, here's the symbol and the value, and so you could see there. That's why I bring up this chart. Just a simple I, like a stick, that's 1. A V is 5, an X is 10, an L is 50, a C is 100, a D is 500, and an M is 1,000. Okay, so if you ever see, like, some marking on the walls and it's in terms of Roman numerals, you can interpret them. But you could see that they kind of went by ones and fives. So 1, 5, 10, 50, 100, 500, 1,000. The next one would be 5,000. But I don't even know if they had a symbol for 5,000. Okay, maybe they added it later in after, like in the Middle Ages or something. But there it is. And then below that over here you see how counting works there. Okay, how their counting works. All right, so there you go. There's the story with Roman numerals. Okay, now we don't use Roman numerals today in our everyday life. Like I said, they're just kind of ornate. We use what are called Arabic numerals, and you'll go, wait a sec, Arabic numerals? I've never heard them called that before. That's the decimal system. Okay, we tend to say decimal system, but they are technically Arabic numerals because they came into Europe from the Muslim world around 960 AD, probably before that, but there is some manuscript that they have from 960 AD, that's over 1,000 years ago, that actually used Arabic numerals. And once Europeans understood Arabic numerals, they go, well, this is so much better than Roman numerals. That was it for Roman numerals. Okay, so just like technology, better technologies will displace older technologies, but there'll still be some around. Okay, so the old technology will still be around. Some of it will be, and the same thing happens with intellectual things like numbers. Okay, so how do Arabic numerals work? Okay, I'll call them Arabic numerals for a little bit, but eventually we'll just call them decimal. Okay, and they work by 10 symbols. Okay, 10 unique symbols. Now, you're familiar with them. In the past, they were written differently, but you're familiar with them. And the most important of these is this one, 0. Okay, 0 is a magical number, and in Arabic numerals, in the decimal system, 0 becomes a placeholder, and you'll see why placeholders are very important. There was no 0 in Roman numerals. There was no reason to have to write a 0. Okay, like if you write out a Roman numeral, nowhere in that Roman numeral is there a symbol which represents a 0. But with Arabic numerals, there is a 0. Okay, and it's a very important number. Okay, because it's a placeholder. But they're in all 10 symbols. So there's like the 9 from 1 to 9, but then with this extra 0 there, 0 through 9 is basically a set of 10 unique symbols. Okay, and you know what values they represent, so I won't go over them. But if I said 3, show me 3 fingers, you would go, there's 3 fingers. Okay, show me 5 fingers, 5 fingers. All right. Okay, how do we count with these? So I made a little table here, just kind of remind you. I'm going to show you a couple of ways in which to think about counting. One is a table, and here's the table. So the way this count works is you start here and you just go from left to right. So there's 0 is your first number, then 1, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then 9, like that. You get up to 9 and you're out of unique symbols. Okay, there is no single symbol. There's no single symbol for 10. For this many fingers. Okay, whoops, there we go. Okay, for that many fingers. Okay, I can't get them all in my camera. But what do you do when you get to 9? Well, up till now you had just a single symbol, and you can think of it as being in just one column. You had to add another column. Okay, And that other column is always to the left. And here it is. It's this right there. It is the number 10. 1 followed by a 0. Okay? And then you can continue counting. But when you count, you repeat in the rightmost column, okay? You repeat the same sequence you had above, 0, 1, 2, 3, 4, 5. But in the leftmost column, you keep that 1. Okay? So here it is, going over. So look at, see the 0 there? That's the same in the, the first row and in that one. Okay? And then you go 1, 0. And then you go 1, 1. So that 1 is just like that 1 there. And then you go 1, 2, and there's that 2 there like that. And you go 1, 3, and there's that there like that. And then you go 1, 4 like that. And then 1, 5, and see the 5 is like that. Now up here, I don't have to write it in here, but you know that you could put a 0 in there like that as a placeholder in front of the 5. Okay, we don't write like that because it there's no reason to put a bunch of symbols, a bunch of zeros, sorry, to the left. Okay, zeros to the right are important, but zeros to the left are not. Okay, and so so we get 15, and then 16, then 17, then 18, then 19. Okay, and so what you should be looking at here is you can see, look at the number on the right. The number on the right, 0, 1, 2, 3, 4, 5, it repeats this entire sequence up to here. Okay, it repeats that entire sequence, 0 through 9, like that. The second one repeats that sequence again, but with a 1 in front. When you get to 19, you have to start over with the rightmost column. Okay, and so that rightmost column goes back to 0, but now the left column you bump up and you get 20. And so you go 20, 21, 22, 23, all the way up to 29. Okay, and once you get to that 9 in the rightmost column, you say, okay, I'm out. I don't have a single symbol past 9. What do? The 9 reverts back to a 0. So when I say the 9 reverts to a 0, I mean the symbol in the rightmost column reverts to a 0, but the symbol in the left column, that 2, gets bumped up to the next one, which is 3. Okay? And then you go through the sequence again, 30 through 39. Okay? And those dots there just mean, because I wouldn't say lazy, but I just didn't want to write out all the numbers. It gets overwhelming. Okay? But you go from 30 to 39. And then once you get to 39, 9 is magic. There's nothing, no single symbol past 9. 9 goes back to 0, and the 3 becomes a 4. And then you go through the 40 sequence, and then you go through the 50 sequence, then you go through the 60s, then you go through the 70s, then you go through the 80s, and then you go through the 90s. And I did write this one out because when you get to 99, you get double magic. So what happens now? Well, this 9 has to go back to a 0. So this is the rightmost symbol, okay, the rightmost column. That goes back to a 0, like that. But then you bump up the next one, and the next one is also a 9. And you go, but I can't go past 9 with just one symbol. So what do? That 9 also goes back to a 0. So this is in the middle column here. That goes to a 0 there. And you have to add a third column to the left, and that bumps up to a 1. Okay? And then you repeat. And you repeat. And so on and so forth. What happens when you get up to 999? Well, then you get triple magic, because the first 9 goes to a 0, and it bumps the next 9 to a 0, which forces the next 9 to bump to a 0, which forces a new column, a fourth column, and that's a 1. So you get 1, 0, 0, 0, and that's 1,000. Okay, and so you're basically running on these cycles. Every time you go through a cycle of 10, you bump up the next column. Okay, and that's the magic of Arabic numerals. So it isn't just, when we say Arabic numerals, it isn't just the shape of the symbols. It's that entire way of counting. Okay, now why is this so great? The reason this is such an amazing way of counting is because you can count to infinity this way. Okay, and every time you get to like 999 now, okay, you bump to 1,000, then 9,999, you bump to 10,000, and you can always keep bumping by adding more and more columns to the left, okay, to the left of the number. And you say, well, when can I stop adding columns to the left? Well, in principle, you can always add a column to the left. In practice, I mean, your number might be bigger than you can fit on a page or something like that, but you can make some really big numbers this way. That's one advantage, okay? The other advantage, which we'll get to later, next lecture is addition. Okay, and so let's continue. All right, so let me show you yet another way to think about this. So I'm going to count using just 2 columns. With 2 columns, you can go from 0 up to 99, because as soon as you get to 100, 100 is the first number that you need 3 columns. And the way to think about this is one column is the ones column. The column on the right is the ones column. You'll see why I call it that in a minute. And then the next column is the tens column. The tens column. Okay. If we had the third column there, I don't, that would be the 100, and then the thousands, and so on. Now, at this point, you might remember this from like, you know, your grammar school. I don't know when they introduced this, but it's pretty early on. Okay, so let's count right now. Okay, and let's look at these columns. Now, I did put the zeros into the tens column, but you could leave them blank if you wanted. Okay, so here's our first number. It is the number 0. Again, I have 2 zeros there, but you only really need the 0 in the ones column. Okay, I just wanted to show you a pattern of what happens in the tens column, which is why I put that 0 there. And you could put it in, it's just that we tend not to. It looks a little strange, but you can. So this is 0. What's the next number? The next number is 1. Okay, and again, that 0 to the left here, like this 0 right here, you could drop it. You could drop it, and I did above. Okay, and now what? Now you have 2, 3, 4, 5, 6, 7, 8, 9. All right, so now we're at 9. And here's where the magic has to happen. We have run out of unique symbols. So this point right here is important. We've run out of unique symbols for the ones column. Okay, and so what do we have to do? That 9 goes back to a 0. So you see that 9 right here? This 9, it repeats. It goes back to the 0. And then the whole sequence from 0 to 9 repeats. So that 9 says, okay, I'm going to cycle back to 0. But if that's all you did, you'd just be counting 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. If you just have one column, it's just like you're counting to 10 or counting to 9 repeatedly. No. What you do, once that 9 ratchets back to 0, it cycles back to 0, you have to go to the next column and you have to say, well, what was the previous number? It was 0? Okay, now it's a 1. You bump up the next column. Okay, that's what I mean by bump. I mean, you just push it up by 1. Okay, so these two things happen together. That 9 cycles back to 0, and the next column cycles from a 1, or not cycles, but bumps from a 0 to a 1. Okay, and then you can continue counting. So then you have 1, 0, which is 10, 1, 1, which is 11, 1, 2, 1, 3, 1, 4, and so on. Notice the ones column is making this kind of cycle: 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and it just keeps doing that. In the ones column, it just keeps cycling 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 over and over and over again. Look at what's happening in the tens column. In the tens column, you have 10 zeros: 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And then you have 1, 1, 1, 1, 1, 1, 1, 1, 1, 1. And then you have, guess how many? 10 twos. And then you have 10 threes, and then you have 10 fours, and then you have 10 fives, and then you have 10 sixes, then you have 10 sevens, then 10 eights, then 10 nines. Okay, so the tens column also does this cycling 0 through 9, but it does it with a periodicity of 10. So you'll have 10 zeros in the tens column before you get to a 1. And you'll have 10 ones in the ones column before you get to a 2. And you'll have 10 twos in the ones column before you get to a 3, and so on. And then, of course, once you get to 99, well, I already told you what kind of magic happens there. This 9 goes back to a 0, and then it bumps that one up. That 9 also has to go back to a 0, and it bumps up the third column, which is the hundreds column that I didn't write in there. Okay, so this is how you count with Arabic numerals or the decimal system. Okay, and that's what I'm saying right here. Okay, why is the second column called the tens column? Because it cycles with a cycle of 10. Okay, the ones column changes every 1. The 10 column changes every 10. Okay, do you want to guess how often the 100s column changes? It changes every 100. The thousands column changes every 1,000, and so on. Okay, and it makes sense because it takes takes a cycle of 10 in the ones column before you bump the next one. Okay, and then you have to do 10 more before it bumps it again. So the tens column required 10 different symbols. It requires you to go cycle through all 10 symbols before it bumps, and so that's why it's the tens column. The next column requires 100, the next one 1,000, and so on. And so from right to left, I know we write from left to right, but I'm just, if you're thinking of the columns from right to left, okay. In other words, starting from this column here first, okay. The smallest column. It's also known as the least significant figure. Okay, and then you move to the right, 100, and then the next one is the first one is ones, then tens, then 100, and so on. So moving from right to left, this is how they work. The first column is, whoops, I went too far. Okay, the first column is the ones column. The next column is first one's the ones column, then the tens column, then the hundreds column. Why 100? Because it's 10 cycles of 10 for 100. The next one would be 10 cycles of 10 cycles of 10, which would be the thousands column, then the 10,000s column, and so on. Okay, and so this is how our decimal system works. All right, now let me just pick an arbitrary number. You could do this with any number. I decided I'm going to show you how to make sense of 5,768. Okay, I just picked a number out of the air. Okay, so what does this number mean, 5,768? The columns are crucial. Okay, what position the numeral is in, the symbol is in, is crucial. So you see that 8 there, it's in the ones column. Okay, you have to identify that. The 6, that's in the tens column. The 7 is in the 100s column, and the 5 is in the 1,000 column. Okay, so once again, the ones, the tens, the hundreds, and the thousands column. Okay, all right. And so here I've got the number written out like this. All right, so I've got, you could see here the 8 is in the ones column, the 6 is in the tens column, the 7 is in the hundreds column, and the 5 is in the thousands column. So you could think of this number as basically 5 thousands. Okay, because that 5 is in the thousands column, you've gone through 5 groupings of 1,000. Okay, and in addition to that, the 7 in the hundreds column, you've gone through 7 groupings of 100. And then the 6, which is in the tens column, you've gone through 6 groupings of 10. And then finally, you've gone through 8 groupings of 1. Okay? And so that number, if you multiply it out, 5 times 1,000 plus 7 times 100 plus 6 times 10 plus 8 gives you this number right here. Okay? That's trivial. And you go, well, why did you show me this? Just so you understand how these columns work. Okay, it might even be helpful to think about this in terms of money. Okay, because we do this with money all the time. Okay, now I know we have $1 bills, we have $5 bills, and we have 20s, and so that kind of messes it up. But imagine that we had a number system where all you had was $1 bill, $10 bills, $100 bills, and $1,000 bills. Okay, how would you give me, if you owe me? I like it when you owe me. If you owed me $5,768, okay, well, you could do a lot of ways. You could give me that many in ones, but if you wanted to do it in the most economical way possible, okay, economical meaning in the fewest number of bills, what would you do? You would give me 5 $1,000 bills. You would give me 7 $100 bills. You would give me 6 $10 bills, and you would give me 8 $1 bills, and that would add up to 5,768. Okay, so there you go. Why was this wonderful? I think I said it already. You can count to infinity, and as you'll see, you can do arithmetic a lot better. Okay, now this business of doing arithmetic a lot better, okay, a lot easier. It's not just easier for our minds. When we make the transition to a mechanical machine, the easier we can make the operation easier. There's a word called algorithm. It means the step-by-step process by which you do something. Okay, if you can make the process that your mind does easier, you can make it into a machine easier. Okay, and so you might say, is there a machine that can count decimal numbers? Okay, and the answer is yes. And you can actually see that machine in older cars. It's what the odometer, the thing that counts the number of miles that you're going. And again, because it's counting, it counts 1 mile, 2 mile, 3 miles, but it has to count up to a lot of miles because cars can go a lot of miles. All right. And so this was called an odometer. And in the old days, they were gears, which I'll describe them to you in a minute. Okay. They were actually gears because the old odometers were mechanical, like literally in terms of gears. Today, they're digital. All right. And so, when you look at your dashboard, it's all LEDs and things like that. But yeah, so you're not going to see like this isn't the odometer in any modern cars. Okay. I don't think there are any modern cars that are using gears for their odometer unless it's some specialized car or something like that. Okay. Anyhow, so let's take a look at, how you could build a machine that counts. Okay. And where are we here? Okay. Oh, let me just mention, here's the wiki page for Arabic numerals if you want to know more about Arabic numerals. Okay, but I pretty much covered everything we need to know. I just wanted to point that out. Okay. And oh, sorry, I skipped one. There we go. Mechanical counters. Okay, so mechanical counters, and you might still see these things around, like this picture right here. Let me just bring that picture up like that. Okay, you've got this thing that you can put in your hand, and you press down on a button, and when you press down on that button, the 7 will become an 8. Then you press down on the button, 8 will become a 9. And then when you press down on that number, that 9 that's in the position of the 7 right now would become a 0. It would go back to a 0, and the 2 would become a 3. And then you just keep clicking on the button there, and it would just count up that way. It would just keep counting like that. Okay, so that's an example of a mechanical counter, and this is how they're built. Okay, now it's a little hard for me to describe this, but basically, take a look at the bottom gear here. Notice that there are these like little edges here, like that. Okay, so it kind of slides, and then there's an edge. It slides, and then there's an edge. Okay, there are 10 of them. And the way this thing would work is it would have to make a rotation. Each gear would have to make a rotation of 10 before it would rotate its neighboring gear by 1/10 of the way. Okay, so let me say that again. So you have a whole bunch of these identical gears, one connected to another. One of them would have to make a full rotation, and its neighbor would make 1/10 of a rotation. Okay, watch how my cursor moves from that edge right there to that edge. Okay, and then again, you'd have to make its neighboring gear would have to make a full rotation, and then you would go to the next edge, and then the gear of the lower significant figure would have to make a full rotation, and you go to the next edge, and then another full rotation to the next edge, and so on until you finally get all the way around. And every time you go around the gear once, you're cycling back. And so the decals that these gears were hooked up to would be the symbols 0 through 9. Okay, I hope that description helps you. I mean, I'm not going to hold you responsible for describing how that works, but I just want to help your imagination to see how you can actually build a machine that can count. And it gets better than that, and that was actually my very first image. And let's go to that image right here. Whoa, something just happened. Hold on. There we go. Okay, so this image here is basically a mechanical cash register, and what you would do is you would put the amount of money in the cash register there, and then you would turn this handle, and this handle turned a bunch of gears, and that's how you could add up how much money you were you owed the store or whatever. Okay, I don't know. I've never seen a mechanical cash register in years. I mean, I was born in 1964, so I did see these things as a child, but I don't ever remember seeing one, in a store recently. Okay, so all right, let's now continue with our story of numbers. Okay, so now what? Well, I had this word Arabic numerals, and the Arabic part, I mean, it depends what you mean by that. Is it the actual symbols themselves, 0 through 9, or is it just the system? So when I said Arabic numerals, I was actually talking about the system of numerals. Okay, now how do they work, or how did they, when they first entered European culture, how did they work? They had 10 unique symbols. Okay, 10 unique symbols. Now you might say to yourself, why 10 unique symbols? Couldn't you have made maybe 7 unique symbols? Or 9 unique symbols? Or 5 unique symbols? And I think the answer is as simple as we have 10 fingers in our hands, okay? 10 fingers. So you might even go back to the Roman numerals. You might say, well, why was 5 special, 5 and 10 special? Well, because we have 5 fingers on a hand. And again, then a 5, and then another 5, and you get to 10, okay? So the 10 is because we like counting on our fingers, okay? That's a pretty obvious reason why 10, all right? But there's no reason why you can't take the Arabic number system and apply it to less than 10 symbols. And so you could apply it to the symbols, only 8 symbols, the symbols 0 through 7, like that, okay? So you can apply it through the symbols 0 through 7. Then you say, well, to yourself, well, how many symbols do you now have? Now you have only 8 symbols. Once you get to 7, you have to cycle back to 0. So this is kind of weird, okay? And I'm not going to hold you responsible for the octal system, base 8 as it's called, okay? But I want to kind of free up your brain for what we're going to do next, and that is look at binary numbers. And so we don't have to do the Arabic number system with 10 unique symbols the way we do in the decimal system. We could use the octal system, which is still Arabic numerals, but only 8 unique symbols. And you go, well, how will that work? Well, first, because there's only 8 unique symbols, as soon as you reach 7, you have to start over in the current column and bump up the next one, okay? So you do 7, and then once you get to 7, the 7 goes back to 0, and you bump the next one. So the 7 is playing the same role as the 9 before, okay? And you go, oh, that's weird. You're right, it is, okay? But the octal system is used. It's used in computers, but you can do this. So once you get to 7, that 7 has to, and that column has to cycle back to 0, and then you bump up the next column. And that means that these columns are in cycles of 8, okay? And so the first column is the ones column. The next column gets bumped every 8, so it's cycles of 8. The next column is 8 cycles of 8, which would be 64. The next column is 8 cycles of 8 cycles of 8, which is the 512. And then the next one would be, 8 cycles of 8 cycles of 8 cycles of 8, which would be 4,096, okay? So it's not ones column, tens column, hundreds, thousands, and so on. It's the ones column, it's the eights column, it's the 64, it's the 512, and the 4,096. Weird, isn't it? Okay, so that's okay. Just try to think about how this system works, all right? So let's try counting in it. So the first column is the ones column on the right. And then the first column to the left is the eighths column, okay? And just like we counted before, we're going to go, so this 0 in the ones column, you could ignore it, okay? We're going to go 0, 1, 2, 3, 4, 5, 6, 7. You get the 7 like that, okay? And once you get the 7 acts like the 9. What has to happen next? The 7 has to rotate back to 0. It cycles back to 0. But when you get this cycle back to 0, the next one has to be bumped up to 1. It has to be bumped up by 1. Okay? And so, all right, so there we go. So then once we get to 7, the next number is 10. Okay, now you're tempted to say 10, but it isn't, because this one here is not in the ones column. That one is in the eights column. Okay? And then you go, let's continue counting. 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7. And we get get to that 7 again. Okay? And oops, I made a mistake here. You get to the 7, and what do? You cycle back to, get to the 7, you cycle back to 0. So that 7 cycles back to, that 7 cycles back to 0 like that. But when that 7 cycles back to 0, you go to the next column, you say, oh, I got to bump that 1 to a 2 like that. Okay? So I agree, strange, but I want you to see the pattern. You get to the end of the sequence, you start over, and you bump the next column. Okay? All bases, whether it's base 10, which is decimal, or octal, or the next one I'm going to show you is hexadecimal, and then finally binary, they all work this way. So now, suppose I say to you, look, you've got this number 1, 2. Okay? You're tempted to say 12. Hold on. I say 1, 2 in base 8. Base 8 or octal. You go, wait a sec, something fishy is going to happen here. Okay? Take a look at this 1 right here. See that 1? What column is it in? It's not in the tens column. It's in the eights column. So this 1 that's highlighted is one grouping of 8. So over here, you have one grouping of 8, or 1 times 8. Okay. This 2, that's in the ones column. Okay. And so that's going to be 2 1s. So the number 1, 2 in base 8, all right, is basically 1 8 plus 2 1s. And if you add that together, that gives you the number 10 in base 10, okay, or in decimal. All right. So it might be a little bit confusing, and like I said, we won't work in octal, but the interpretation of the number here, 1 2, is the symbol 2 has its interpretation because it's in the ones column. The symbol 1 has its interpretation because it is in the eights column. Let me do another example and then we'll move on. 362 in base 8. Okay, so 362. Don't think of this as 362 like you do in decimal, because if you're thinking that, you're thinking, oh, this 2 is in the ones column, that 6 is in the tens column, like 60, and this 3 here is in the hundreds column, like 300. No, that's true in decimal, but not in base 8. In base 8, that 3 is in which column? Well, it's in the third column, and the third column is the 64 column. Okay, so over here, that 3, it's in the 64 column, so we have 3 groupings of 64. 3 times 64. This 6 here is in the eights column. So in addition to the 3 groupings of 64, we also have 6 groupings of 8. Okay, and then we have this 2 here, like that, and that's in the ones column, so we have 2 groupings of 1. And so 3 groupings of 64 plus 6 groupings of 8 plus 2. In other words, 3 times 64 plus 6 times 8 plus 2 is equal to 242 in decimal. And let me say that right here. Okay, that's in decimal. So, don't just look at the, again, I'm not going to test you on base 8, but if you look at base 8, if I tell you this is base 8 here, you don't look at this number and say, oh, 362, like 3 100s, 6 10s, and 2 1s. No, you look at that number and you say, oh, 3 64s, 6 8s, plus 2 1s. And then that turns out to be 242 in decimal. Now, for that number, you can interpret it as 2 100s, 4 10s, and 2 1s because it's in decimal. Okay, so here the columns are 1, 10, and 100, but over here the columns are 1, 8, and 64. Okay, we don't use this system in our day-to-day lives. We could, your minds have to change, but everyone, since over 1,000 years, have interpreted it in terms of decimals. So they always interpret the columns. You don't have to be told this is decimal or octal. It would drive our society crazy. When you give someone a number, it is automatically understood that that number is in decimal, meaning that, this column here, okay, that 2 is in the ones column. This 2 is in the tens column. That 2 is in the hundreds column. But if you use base 8, this 2 would be in the ones column. That 6 would be in the eights column. That 3 would be in the 8 times 8 column, where the 64. Okay. Now, you might say, oh, all right, if you get that, you go, okay, well, like at the beginning I said here, why 10? Why not 7? Why not 9? Why not 5? Well, you know what? Why not more than 10? Can we do more than 10? And the answer is yes. There's no reason why you have to only use the unique symbols 0 through 9. You can add new symbols. Okay, and so there is another numerical system, and I'm very familiar with this one because of my work in computers. It's known as hexadecimal. And hexadecimal has 16 unique symbols. We can either say base 16 or hexadecimal. Okay, so it doesn't really matter, one or the other. Okay, whether you say base 16 or hexadecimal, we mean 16 unique symbols. You say, well, how would you create 16 unique symbols? And here they are. From 0 through 9, that's 10 unique symbols. We'll just use the old Arabic numerals, and then we'll add A, B, C, D, E, and F. Okay, and you go, wait a minute, how am I supposed to interpret A? Well, how many things are there after 9? There are 10. This many. Oh, I'm sorry, I can't put my both hands in. There we go. There we go. There we go. You can see. All right, 10 fingers. Okay. So in decimal we say 10, but in hexadecimal we just say A. You say, show me A fingers. Here you go. Here's A fingers. Okay. Show me B fingers. I can't do that. That would be 11 fingers in decimal. But B is interpreted as the number 11. C is interpreted as the number 12, 13, 14, and 15. F is 15. Once you get to 15, once you get to F, you have to start the cycle over again. Okay, and so here, this just basically says what I just said. A represents 11 in decimal. B represents 12, C represents 13, D represents 14, E 15, 14. Oh, I made a mistake, guys. I apologize. A is 10. Let's get this right. B is 11. C is 12. 13. E is 14. And F is 15. There we go. Now I've got it right. Okay? All right. Okay. I'm not going to test you on this. I'm just trying to free up your brain so that when I get to binary, it's going to seem natural. Okay? So in this system, the columns from right to left. I know we write from left to right, but it's easier to think for this in terms of right to left. Okay, so starting on the right, moving to the left. Okay, your first column is your ones column. Your next column is, well, how many unique symbols do you have? 16. Okay, so your next column is the 16 column. Okay, and then before you get to the next column, you have to have 16 cycles of 16. Okay, and so 16 times 16, the third column is the 256 column. And then the next column is 16 cycles of 16 cycles of 16. That is the 4096 column, and so on. Okay, so very different columns. All right. Now, if we take a look at 1C in hexadecimal, you go, 1C, I've never seen a number like that. I've never seen a number with a letter in it, 1C. Well, you might, like for serial numbers and things like that, but like for counting numbers, you've never seen that. Again, because we only use decimal. But if we used hexadecimal, 1C would be interpreted this way. That 1, what column is it in? It's in the 16 column. So that 1 means that you have one grouping of 16. Okay? And that C says you have C groupings of 1. But what is C? C over here represents 12. So I actually made a mistake here. I'll fix that in a minute. C represents 12. So over here, this should be 12 like that. So that C says I have one grouping of, I have 12 groupings of 1. And so the number turns out to be 28 like that. Okay? So think about that for a second. Basically, the 1 is in the 16 column. The C, which represents 12, is in the ones column. So 1C basically says I have one grouping of 16 plus 12 groupings of just 1. And 116 plus 12 ones is 28. So 1C is equal to 28 in decimal. Okay, what about the next one? I think I might have made the same mistake here. B is actually 11, so this should be 11. And the 5, 16, that's right, and 0. Okay, so I just had one wrong here. Let me just quickly do that calculation on my calculator here, and I'll fix it for you. There we go. Okay. So it turns out that the number is actually 2,897. Let's see if we can understand that. So the number we're looking at is B50. Okay, B50. You say, how do I interpret that number? Well, I have to tell you it's hexadecimal. Okay, so B50 in hexadecimal. What is that? Well, that B, what column is that B in? That B is in the third column, and the third column represents 256. Okay, so we have 11. B is 11. So we have 11 groupings of 256, or 11 times 256. Okay, so there we go. 256. That takes care of the B. All right. That 5, what column is that 5 in? All right. This is hexadecimal. So that that column there, the second column over, is in the 16 column. So we have 5 16s. And then that 0, what column is that 0 in? It's in the ones column, so we have 0 ones. Okay, so once again, B50 is B, in other words, 11 256s. Okay, grouping of 256, 5 16s, and 0 ones. 0 ones. Okay, and that turns out, I just did it on my calculator, 2,897 in decimal. Now in the decimal, the symbols are interpreted differently because the columns are different. That's the ones column, that's the tens column, that's the hundreds column, that's the thousands column. In hexadecimal, that's the ones column, that's the 16s column, that is the, well, that is the 256 column. All right. So you could see that you could extend this to any number system you want. Okay, and like I said, because of computer science, I'm actually pretty good in hexadecimal. And let me just count for you in hexadecimal so that you get how this is working. You could hear, I mean, there's a lot of numbers that I have to say, but you could hear the cycle in there. So let me count for you in hexadecimal. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F. 1 0 1 1 1 2 1 3 1 4 1 5 1 6 1 7 1 8 1 9 1 A 1 B 1 C 1 D 1 E 1 F. 2 0 2 1 2 2 2 3 2 4 2 5 2 6 2 7 2 8 2 9 2 A 2 B 2 C 2 D 2 E 2 F 3 0 and so on. Notice that when I got to 2 9, 9 was not the end. 2 9 is followed by 2A 2B 2C 2D 2E 2F. F is the end. So after 2F we go to 3 0. Okay, so crazy, right? And that's how Arabic numerals can be extended beyond base 10, beyond decimal, to either be octal, or not either, but one possibility is octal, 8 unique symbols, hexadecimal. I mean, I don't know, like if there were alien cultures with like 7 fingers, I guess that would be called heptadecimal. Okay, it was a base 7 and so on. And so you could imagine all different types of number systems. Okay, still Arabic numerals. They still use the Arabic numeral system, but the base, that is how many unique symbols you have, is different. Okay, now why did I do this? Why did I throw all this at you? Okay, because I kind of wanted to free up your brain, because remember, what's this mechanical machine that I'm building? This little adding machine that we're heading towards. What is it? How does it work? And it works, or what is its working parts? It works because of switches. Ones and zeros, okay, these switches, on or off, all these switches which are on or off. And now you think to yourself, I've got this new way of thinking. New way, I mean, I've been doing it for 1,000 years, but this Arabic numeral way of counting. And I could do it with 10, and I like doing it with 10 because you're used to it, because you've got 10 fingers, okay? But suppose we had just 2 fingers, okay? Can we count with just 2 fingers? And the answer is yes. Okay, this is base 2. All right, so there are only 2 unique symbols. It's known as binary, and the 2 unique symbols are 0 and 1. All right, and remember, the unique symbols, once you get to the end, you cycle over. So in decimal, when you got to the 9, you had to go back to 0. In octal, base 8, when you got to the 7, that was the last unique symbol, you went back to the 0. Okay, and in hexadecimal, you got to the 9 and you weren't there yet. You got A and then you went all the way to F. F was the last symbol, then you cycle back to 0. Here the last symbol is 1. As soon as you get to 1, you have to cycle back to 0. Okay, and so everything's in terms of 2s. And so over here, the columns are the first column, again, from right to left, okay? So I know we write from left to right, but thinking about it from right to left, the first column is your ones column. The next column is your 2s column. The next column is your 2 columns, or your 4s. The next column is 2 groupings of 2, which is your 8, then your 16, then 32, and so on. Already you're starting to see something. Whoops, let me scroll that down a bit. Okay, there you can see it. Okay, already you're starting to see this pattern in terms of powers of 2. And if you go out and buy a USB drive, you'll see that you could buy, I don't know if they still sell them, because 32 gigabytes is kind of small, but you could buy a 32 gigabyte, okay? And you could go, well, I need the next size up. The next size up is not 33, it's not 34. Guess what the next size up is? It's 2 times 32, or 64. And you go, okay, well, I'll buy a 64. And you go, well, that's not big enough. I need more. So guess what the next size up from 64 is? It's not 65. It's not 67. It's not 100. Okay, it doesn't go by powers of 10. It's not like you can buy 100, 150, 200, or anything like that. After the 64, the next one's 128, and 128 is 2 times 64. It's all by powers of 2. And you go, why is it all by powers of 2? Because the underlying circuitry are these switches. Okay, they're switches, and every time you add like another series of switches, it doubles the memory capacity of that USB stick. Now I'm picking a USB stick just by just as an example, but like everything in computers are in terms of powers of 2. Okay, let me teach you, and this is the last thing we'll do for our lecture, for this lecture, is that let me teach you how to count in binary. Okay, so how to count in binary. So what I have here is a table, and I've spread it out because this you are responsible for. Okay, what I have in this table is over here. These columns are your binary number columns. Okay, so your binary number is going to be pretty spread out. Okay, I did that on purpose. Okay, and so the leftmost, the rightmost is 1. The next one to the left is 2, the 2's column, and then the next one is the 4's. The next one is the 8. What would the next one be? 16. Then after that, 32. Then after that, 64, 128, and so on. Okay, so getting bigger and bigger and bigger. Okay, so great. So that grouping right there, they're the columns for the binary number, and everything below them is binary number. Over here, to compare, these are your decimal numbers. Okay, so if you take a look, let me scroll down, you can see the decimal numbers. They go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, then 10, 11, 12, 13, 14, all the way up to 15. So that this column here is basically just the regular numbers that you're familiar with. And these 4 columns here, okay, they are the binary numbers that I'm going to teach you right now. Okay, so let's start. So the first number in all of these number systems is 0. Okay, 0 binary is 0 decimal. It just means nothing. Okay, the next number is 1. All right, so there it is. And 1 binary and 1 decimal are the same. Okay, now the next number in decimal is given the symbol 2. There it is. Okay, like 2 fingers like that. Okay, 2 fingers. All right, but that's not how you write 2 in binary. What happens? Remember, when you get to the last symbol in the sequence, you got to start over. But the last symbol in our sequence in binary numbers is the 1. And so, right here, we're at a 1. You go, well, what comes after the 1? Not the symbol 2. See, after the 1, in decimal, the next symbol is 2. No, there is no symbol after 1. You're done with all the symbols. So what you have to do is you have to cycle back to the original symbol, which is 0. And so then you're back to 0 like that. And you go, well, that was pretty short. Yeah, that's right. It was short because there's just 2 symbols. And so you're counting, you go 0, okay, great, and then 1, and then you go, uh-oh, I'm at the end of my sequence, go back to 0. But as soon as you go back to 0, what do you have to do? So when you cycle, like in decimal, when you get to the 9, you go back to 0, you have to bump the next column over. Well, the next column, I didn't write in here, like right there, and there. Oops, there. I didn't write, you can see where my cursor is. Oh, yeah, I guess you can't see it here. Right here, like where this cursor is. I can put a temporary 0 in there like that. See that 0? I didn't write that 0 in, okay? Okay, and I didn't write a 0 in there, okay? But you can imagine that there was a 0 there. And so when you get to that, when you're at that 1 and you rotate back to 0, you have to bump up the next column. That column was a 0 before. Right here, there was a 0. And what happens is that 0 has to get bumped up to a 1, and there it is. Okay, so you went from 0 to 1. So when the 0 rolled back to, when the 1 rolled back to 0, this 0 had to be bumped up to a 1. Okay, and now we're at the next number. So 2 in binary is 1 0. Okay, 1 0. So if I say how many fingers do I have up, you might say in decimal 2. But if you were writing it in binary, you would write 1 0. It looks like the number 10, but don't think of it that way, because the 0 is in the 1's column and the 1 is in the 2's column. Okay, so there we go. So there's 2. And then you say, okay, well, what's the next number? What's the next number after 1 0, binary 1 0? Well, the next number is, take a look. You always start with the rightmost column. You say, well, what's the number after 0? Well, it's 1. Okay. Now, from going to 0 to 1, there's no bumping of the the column to the left. Okay, and so that 1 just stays a 1. Okay, as that 0 goes from 0 to 1, that 1 stays a 1 there like that. So 1 0, and then the next number is 1 1. Okay, so this many fingers in binary is written as 1 1. Don't think of it as 11. I know you're tempted, because you're tempted to think of this is a 1's column and that is the 10's column. But in binary, if we're in binary, that column is the 2's column. Okay, good. So 1 1 is 3. Okay, now what? This is kind of like our 99 in decimal. What do I mean by that? Well, 1 is at the end of the line, and you got to cycle over and bump the next column up. So you take a look at that 1 there and you go, well, what's the next number? Now you got to cycle back to 0. So after the 1, you cycle back to 0. And what do? When you cycle back to 0, you bump the next column over, up. So this 1 here gets bumped up, but you're at the end of the line. So even that 1 cycles back to 0. Here it is. And when you cycle back to 0, you got to bump up the next column. And the next column over here, that was 0. And what do? You bump that 0 up to 1. Okay, so there you go. And so now 1 0 0, that is this many fingers. Okay, that's 4 fingers. Okay, 1 0 0. I know it looks like the number 100 in decimal, and again, because you're interpreting the columns as 1, 10, and 100. But in binary, the columns are the 1's column, the 2's column, and the 4's column. Okay, so 4 is 1 0 0. Okay, let's continue counting. So you always, when you count, you always start in the 1's column. You say, well, what comes after the 1? Sorry, what comes after the 0? 1. Okay, there it is. What comes after the 0? The 1. Now, when you go from 0 to 1, that's it. You don't go over to the next columns because you didn't cycle. You just went from 0 to 1. Okay, and so that means that when you went from the 0 to 1 here, that was sufficient. You don't touch that one. You don't touch that one. And all the other ones, by the way, to the left are all zeros. Okay, I didn't write them in, but they're all zeros. Okay, and you go, okay, great. So we're at the next number. What's the next number after 4? It is this many fingers. Okay, 5. And so 1 0 1 in binary is 5. Okay. All right, now what? Yeah, again, you always start when you're counting with this column right there, the 1's column. What's after 1? You cycle back to 0. So this 1 cycles back to 0, but when it cycles back to 0, you bump the next column over. So that means you go from 0 to 1, and 0 to 1, that's it, you're done. You don't bump anymore, and so that 1 in the next column stays a 1. Okay, let's do that one more time. So you're at 101 like this, and we're counting. So that 1 cycles back to 0. You have to bump the next column, so the 0 goes to 1, and that's it. There's no more cycling of the next column, so that 1 stays as a 1. Okay, and so 101 was 5. 110 is 6. That is this many fingers. Okay, oops, there we go. So yeah, 5 and then one more. Okay. All right, so 110 is 6. Okay, and now what? Well, we're gonna count, so always start from the 1's column. 0 is followed by a 1, and did we cycle? No, so leave all the other columns alone like that. Okay, so 111 is 7. And now we are in another one of these interesting situations, because we have all 1s, and that's like in decimal, that would be the equivalent of kind of like not in value, but in terms of the mechanism, it's kind of like our 999. Okay, because all of them are going to cycle back. All the 9s are going to cycle back on the next number. And so over here, that 1, what comes after 1? Well, you cycle back to 0. But when you cycle back to 0, you got to bump the next column. Okay, so that next column was a 1, and we're bumping it by 1. Uh-oh, we got to cycle that one back to 0. Okay, so bump the next column. That's also a 1. Okay, that's a 1. So now what? Cycle that one back to 0, and then go to the next column, and that next column was a 0, and it becomes a 1. And when you go from 0 to 1, that's it. So when you go from 1 to 0, you have to bump the next one because you're cycling back. But when you go from 0 to 1, you don't touch the columns to the left. All right? So 1 0 0 0 is 8. Let me go through that logic one more time for you. Okay? this 1 cycles back to 0, bump the next column. That 1 goes back to 0, bump the next column. That 1 goes to 0, bump the next column. 0 goes to 1, no more bumps. Ta-da! Okay. How do you get 9? Well, I hope you're starting to get the hang of this. That 0 goes to 1, no more bumps. So this piece of the number and that piece of the number stays the same. One more time. 0 goes to 1, no bumps. So this part of the number and that part of the number stays the same. So 1, 0, 0, 1 is 9. Okay. And then, how do we get 10? Well, that 1, cycle back to 0, bump the next column. 0 goes to 1, no more bumps. The rest of the number is the same. Okay. So 1, 0, 1, 0 is 10. All right, great. Let's continue. So we're at 10, 1, 0, 1, 0. That 0, the next number after 0 is 1, and we didn't cycle, so the rest of this number stays the same. You can see there that piece and that piece. There were no bumps to the left. 0 goes to 1, that's it, no more bumps to the left. So that's 11. 1, 0, 1, 1 is 11. Okay, next number. The 1, cycles back to 0, bump the next column. 1 cycles back to 0, bump the next column. 0 goes to 1, no more bumps. The rest of the number stays the same. 1, 1, 0, 0 is 12. All right, continue. The 0, the next number is 1, no bumps. So that means that this part of the number and that part of the number stays the same. The only thing that changes is that 0 goes to 1. And so we have that 1, 1, 0, 1 is 13. Okay. And then next, 1, 1, 1, 0 is 14. How did we get that? 0. Next number is cycle back to 0, bump the next number. 0 bumps to 1, and that's it. No more bumps after that. This part of the number and that part of the number are the same. Finally, that's so 1, 1, 1, 0 is 14. Finally, we're going to get to 15. That 0 goes up to 1, and there are no more bumps to the left, okay? Because 0 to 1, it didn't cycle. There's no cycling, no bumping to the left. And so 1, 1, 1, 1 is 15, like that. All right. So there you go. Could we continue this? Yes, we could. What would the next number be? Let's see if we can do that next number. Well, the next number, of course, is going to equal 16. But starting from the left here, the 0, what does it do? It cycles back. I'm sorry, guys. The 1, what does it do? It cycles back to 0. Bump the next one. That 1 cycles back to 0. That 1 cycles back to 0. That 1 cycles back to 0. And you have to go to the next column, and that next column is a 1. Move that over a little bit like that. Okay, so 1, 0, 0, 0, 0. That's going to be 16, like that. Okay, I don't want to continue this because I think you've got how this works. So basically, you start with the ones column. You look at the ones column first, and you increase it by 1. Now, if you go from 0 to 1, you're done. Leave the rest of the number the same. But if you go from 1 to 0, you're cycling back to 0, bump the next column over. If the next column also goes from 1 to 0, bump the next one, and it just cascades until finally you get to the point where you're just going from 0 to 1, and 0 to 1, that's it. The rest of the number stays the same. Okay? And that's how you count. Let's look at some patterns here. Let's look at some patterns. So look at the pattern in the ones column. This is base 2. So that means that it just takes 2 numbers before you cycle back. So it goes 0, 1, 0, 1, 0, 1, 0, 1, and so on. So the ones column, you see 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay. The twos column, how does that work? Well, I didn't have the 0 here. I'll put it in right now. Okay, I'll put that one in. But you could take a look in the twos column. You go 0, 0, and you go 1, 1. Then you go 0, 0, and let me scroll down. You can see here. Then you go 1, 1, then 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1, and so on. Okay, so in the twos column, it's in cycles of 2. You do 2 zeros, then 2 ones, then 2 zeros, then 2 ones, then 2 zeros, 2 ones, and so on forever. Okay, what about the fours column? Well, I didn't put the zeros in there, but here you would have 0, 0, whoops, 0, 0. So you would have 4 zeros, 0, 0, 0, 0, and then you, 4 zeros followed by 1, 1, 1, 1, then 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0. I think you get the pattern. It's going to be 4 zeros followed by 4 ones followed by 4 zeros. It's cycles of 4. Any guess for the eighths column? 8 zeros followed by 8 ones followed by 8 zeros. The 16 column, which is the next one over, 16, 2 times 8, right? So 16's column is going to be 16 zeros followed by 16 ones and so on. And it goes on like that. Now, it's really interesting because if you take a look at this number here, 0, 0, 0, 0, okay? And you take a look at 8 down here, that's also, so this, let me say that again. This one is like a 0 in the eighths column, followed by 0, 0, 0 in the 4, 2, and 1 column, okay? And this one is 1 followed by 0, 0, 0, okay? The next number is a 0 in the eighths column, followed by 0, 0, 1. And then if you go down to the next number here, it's a 1 followed by 0, 0, 1. Okay, and then over here you have a 0. The 0 that I'm mentioning, that's the first 0 over here, which I didn't draw in. Okay, so you have a 0 in the eighths column followed by 0, 1, 0. Okay, and then if you go 8 numbers later, sorry, 4 numbers later, okay, you've got a 1 followed by 1, 0, 1. In other words, what I'm trying to show you, make it brief, this entire pattern here, all right, that entire pattern there is repeated again. Sorry, I missed one. I got to do it right. This entire pattern here, up to and including the 7, okay, that entire pattern there is repeated again here. But the only difference is for the first group, you had a 0 in the eighths column. For the second group, you had a 1 in the eighths column, okay? And so there's these patterns that you can see in how binary numbers work, all right? And so there it is. That's how you count. You know, for counting, I think it's good to memorize or understand how you can count from 0 to 15, okay? Or maybe even 16, because, you know, here, when we get to 16, you can see that. But, you know, beyond that, I don't think it's important because the numbers start to get big, okay? But you should understand this process of counting from 0 to 16 in binary, okay? And just to recap one more time, you start from, let's pick a number here like 9. You start from the ones column. You say, well, okay, what's after 1? Cycle back to 0. If you cycle back to 0, then you have to go to the next column. The next column is 0. What's after 0? A 1. Well, is there any, did you cycle back? No, from 0 to 1 you didn't cycle back, and so the rest of the number stays the same. In other words, this number here, sorry, this number here and that number there stay the same. Okay, so there you go. Now, at this point you might say, well, okay, how, you know, what am I responsible for here, like on a test? Okay, what kind of questions would you ask on a test? All right, so mostly here what I would ask is, and that's what we're going to practice for the rest of this lecture, mostly here what we would practice is converting from binary to decimal. I'm not going to ask you to go from decimal to binary. I'm going to give you a binary number and I'm going to ask you convert that binary number from binary to decimal. It's not hard to go from decimal to binary, but I don't want to overburden you, okay? I'm trying to teach you the bare minimum to accomplish the goals that I mentioned at the beginning. I want to show you how to build an adding machine in binary, okay? So, better yet, how to build an adding machine using switches. Okay, so let's convert these following numbers from binary to decimal. So there's this first group here. Let me copy and paste them down here. Okay, so like this. And let's convert those first. Okay, so the first one, 1, 1, you can convert in a couple of ways. I'm going to show you 2 ways to think of this. It's a really short binary number, okay? And I just said that you should know how to count from, you know, 0 to 16 in binary. And so, you know what? You could just have memorized that 1, 1, like that, is 3. Okay, just like that, right there. So 1, 1 is simply 3, okay? These zeros that I had in front here, let me get rid of them right now. And the reason I put them in there was to just help you understand, you know, how this system works. But we usually don't write the numbers to the left, okay? So 1, 1 is 3. There, done, converted, okay? So 1, 1 equals 3, all right? And that's good enough. That would answer the question. 101, you could just go to the chart again and you go, oh, 101, that's 5. Okay, you should have it memorized. It's not as hard as you think. Okay, right now I'm guessing that this feels very strange to you, but it's really not as hard as you think. Okay, once you go over them a few times. So 101, that is 5, and so you go, okay, well I have that one memorized, so it's 5. like that. And then 1, 1, 1, you go up to the chart here and you go 1, 1, whoops, 1, 1, 1, that's 7. That 0 to the left of the number doesn't count, so it's just 1, 1, 1, or you could drop it. And so that's equal to 7, and there you go. You've converted those numbers. There's another way to convert them, okay? And I want to show you that now because it leads to how to convert the bigger numbers, okay? So one way to convert is you take a look at this 1, 1 here, and you realize that the column, how you interpret the ones and the zeros, has to do with what column they're in. Just like we did with decimal, just like we did with octal, just like we did with hexadecimal, okay? The column is everything. So this column here, let me see if I can put the number. That column there, oops, that column there is the ones column. Actually, I'm going to put it right underneath, okay? So you see that 1 here, underneath that 1 there? That just says that's the ones column. Or I guess, you know what, let me do this a little bit better, because above we put the columns on top. I can do that here, okay? So that 1 on top of the 1 in the binary number, okay, that says it's in the ones column. What's the column just to the right of it? Well, that column is the twos column, like that, okay? So these numbers that are highlighted, they're decimal numbers, okay? So we've got the ones column on the right and the twos column on the left. So you know the way you interpret this number here, and I'll do that underneath, is you say, okay, I have 1, 2, okay, so I have 1, 2, like that, plus I have 1, 1, like that. All right, so what did I just do? I said, okay, I have 1 grouping of 2 and 1 grouping of 1, okay? Well, 1 times 2 plus 1 times 1 is, ta-da, 3, okay? And we get the answer that we expected, the answer that we had memorized, okay? All right, good. Let's do the 5s column. So over here, this is the 4s column, that's the 2s column, and that's the 1s column. Again, these numbers that are highlighted, they're not binary, they are decimal numbers. They're decimal numbers, okay? And so what this is saying, so this is just mnemonic, okay? Mnemonic meaning is just a way for us to, help our brains. That says there's 1 in the 1s column, 0 in the 2s column, and 1 in the 4s column, okay? And so how do you work that one out? Okay, let me do that over here. So I have 1 in the 4s column, 1 in the 4s column. I have 0 in the 2s column, okay? See, 0 in the 2s column, so 0 in the 2s column. And I have 1 in the 1s column. 1 times 4 plus 0 times 2 plus 1 times 1 is, ta-da, 5. Okay? Getting the hang of it? So what about the next one? Well, the next one, this is the 4s, the 2s, and the 1s column, okay? And at this point, you can get fast about this. You either have something in the column or you don't. So this says I have a 4. I have a 4. Okay, great. So, because, 1 times 4 is just 4, okay? So 1 times 4, I'm just going to skip a step very quickly. I have a 4. I have a 2, right? I have 1, 2, and I have a 1. 4, 2, and 1 is 7. All right, there you go. Okay, converted that number. So you can either have them memorized, or you can you can just convert them this way. Now, why did I show you this? You say, oh, just look it up in the chart. Well, because we're going to have more fun. Here's the more fun part. Let's convert those. Okay, let's convert those. I don't know if we have to do all of them. Okay, I have them there because I just wrote down a bunch of numbers, but it's probably not necessary to do all of them. Let's let's just do 3 of them. Okay, like that. Okay, so the first one. All right, so let's do our little mnemonics again. Okay, this column is the this column is the 1s column. This column is the 2s column. That column is the 4s. The next one over is the 8s column. Okay, like that. All right. So I hope that's not too messy for you. I could separate the spaces just this one time. Okay, like that, and say, okay, so that one is in the 1s column, that one is in the 2s column, that one is in the 4s column, and that one is in the 8s column, like that. Okay, but we usually just write the numbers together. Okay, like that. And now what? Well, if we're going to convert this number, you would say I have 1, 8, plus I have 1, 4, plus I have 1, 2, plus I have 1, 1. You say, how did you do that? How did you get that? I have 1, 8. Okay. I have 1, 4. I have 1, 2, and I have 1, 1. Okay, and that's what I said here. You add them together and you get 15 like that. Okay. If I were to do it quickly, why bother with the ones like one time? You know, I'd say I have an 8, I have a 4, I have a 2, and I have a 1. And so you could just equivalently say I have an 8, I have a 4, I have a 2, I have a 1. That's equal to 15. Okay, and that converts that number there like that. All right, let's convert this number. Same thing. Okay, so we've got this. Let me just do a quick copy and paste here. Like that. Okay, what does this say? I have an 8. Whoops, I have 1, 8. How many 4s do I have? I have no 4s. I have 1, 2, and I have no 1s. Okay, so to convert that number, I'll do it right here. I have an 8. I have 1, 8. I have no 4s. I have no 4s. I have 1, 2, and I have no 1s. I have no 1s like that. If I add them all together, that's an 8 plus a 2, right? Because 0 times 4 is 0, and 0 times 1 is 0, and that's equal to 10. Okay, that's 10, but careful, that's decimal 10. All right, so that is this many fingers. Okay, my full complement of fingers. All right, there we go. All right, let's I hope you're getting the hang of this now. Let's convert this one. Okay, and we can convert it pretty quickly because I think I'll just put the mnemonic down one more time just so we can get it straight, but I think you're getting the hang of this. So you have 1, 8. So you can just write that down. I have an 8. I have 1, 4. There we go, we have a 4. I have no 2s. All right, so I just skip that one, and I have 1, 1, like that. And you say, well, what's that equal to? 8 plus 4 is 12, plus 1 is 13. There we go, 13. And by the way, this is also in our charts, which you can memorize. Okay, so that was the other way to do this, is just memorize it. But 1101 should be 13. Is it? Let's go back to our chart here. 1101. Here it is. 1101. Ta-da! It's 13. Okay. Great. And I think that's good enough. I mean, I had another one. You know what? Let's do one more. Let's do this one right here. Let's do that one right there. Okay. And I could do that one down here. And I'm even going to skip the mnemonic. I'm just going to, this is the way I do it. I'm going to say, okay, I have an 8. Great. I have a 4. Great. I have a 2. Great. How many 1s do I have? None. That's it. I'm done. 8 plus 4 is 12, plus 2 is 14. Okay, and we're done. And again, just to show you that it matches in the chart, 1110 is 14. Okay. When the numbers get bigger, the only other thing I said, this is how I do it. One tiny difference: when the numbers get bigger, I start from the left and I move right. And the reason is that I know this is the 1s, 2, 4, 8, 16, 32. When the number gets very, very big, I kind of get lost which column it's in. So I have to start at the right and move over. Okay, and it's just a slight difference. I might do that for my next numbers. Okay, so these numbers, they're beyond 16. Okay, they're bigger than 16. You go, well, how do I convert those numbers? And it's the same idea. So I don't want to do too many of them. Let's just do this one right here. Okay, you say, how do I do that? So over here, let me just separate these out. All right, I won't do this. I'll do another one, but I won't do this for all of them. And you go, okay, well, now what? So now this is the 1s column right there. This is the 2s. That's the 4. That's the 8. Okay, that's the 8 right there. And this one, you say, well, what's that one? That one is the 16s. Okay, that's why I separated them out. That's the 16s column. And so you could say, okay, I have a 16, right? I have 1 16. I have no 8s. I have a 4 and a 2 and a 1. And you say, what's that equal to? 4 plus 16 is 20. 22, 23. And so that's equal to 23. Okay, like that. And again, I did start on this side, but let me do another one. I don't know. Let me do this one right here. Okay, copy. And let me put that underneath. Well, oops, I missed one of the digits. There we go. How would I do this? I actually would start right here, and I would go, I have a 1. And then I would go to this one, and I go, that's in the 2's column, I don't have that. And then I would go to this one. That's in the 4's column, so I have a 4. Then I would go that one. That's in the 8's column, I don't have anything. And that one's in the 16 column, and I would say, okay, that's 16. Just like that, okay? And you can see now this is pretty easy, okay? I have a 1 in the 1's column, great. I have no 2's. I have 0 in the 2's column, so don't even write down the 2 there. I have 1 in the 4's column. I have no 8's, and I have a 16. Okay, and there it is. So now 16 plus 4 is 20, and that's the number 21. Okay, and you can see that now we're beyond the chart because the chart just went up to 16. Okay, we're beyond the chart. So these are beyond the numbers that you would memorize. Okay, and so on. It might be worth doing one more in with up to the 16th column. Then I'll do a really big one. Okay. Okay, so how would I do this one? What column is that? The 1's column. Okay, I have a 1. Next, what column is that? That's the 2's column. I have a 2. What's that? That's the 4's column. I have no 4. Skip it. That's the 8's column, so I have an 8. That's the 16's column, so I have a 16. And let's add that up. 16. 16 and 8 is 24. 25, 26, 27. Okay, I think I did that right. And 26, 27. Yeah, okay, there you go. So 11011 binary is the same as 27 decimal. Okay. All right, let's do some larger ones. Let's do this one here. All right. And let me paste that and go, how would I do that one? Okay, so same thing. I have no 1's, I have no 2's, and I have no 4's. I have an 8 right here. I have an 8. When I say I have an 8, why do I know that? Because I have a 1 in the 8's column. I have no 1's because there's 0 in the 1's column. I have no 2's because I have 0 in the 2's column. I have no 4's because I have 0 in the 4's column. I have an 8 because I have a 1 in the 8's column. How many 16's do I have? None. And what column is that? Well, 1, 2, 4, 8, 16. What's after 16? 2 times 16 is 32, so I have 32. Okay, so a 1 in the 8's column, a 1 in the 32 column, that is 40. So 1, 0, 1, 0, 0, 0 in binary is equal to 40 in decimal. All right, and there we go. I'm going to stop the lecture at this point, because I think this is more than enough information for you guys to digest. I will put up, in addition to your assignment, I will put up just practice quizzes. And they're not quizzes. They're quizzes as far as Canvas is concerned, but they're just like assignments. Okay, but they're not even. I'm not going to count them, and I will put beside them practice. And you could just practice converting over and over and over and over again. And then I think I'll put up 40 questions, and you'll go, "This is boring. I get how this works." They're multiple choice. I get how this works, and then you're done. Okay. As soon as converting becomes boring for you, it means you get how this works. Okay, and then next class, next lecture, I'm going to show you how to add and multiply with binary. Okay, and it's not as hard as you think. All right, I'll show you how to add and multiply. I will also show you how to do long division, subtract and do long division in binary. I will not expect you to do long division in binary on a test, but the reason I want to show you is I want to show you that it's easy in binary. Binary looks weird because you're not used to it, but if you got used to binary, you would find all of your arithmetic much easier in binary than in decimal. Okay, and so you say to yourself, okay, why don't we all just switch over to binary? Well, it would be very hard. You can imagine how hard that would be. But if we did, in like in your grammar school, okay, I don't know when you learn to divide, probably like grade 3 and 4. Okay, when you learn not long division, it would be so easy. You would learn that, very quickly. Okay, we don't do that because we're used to decimal. Okay, enough of that story. But the fact that it's easier is important because remember, we're trying to make a machine that does long division. The fact that it's easier, that the algorithm is easier, means that you can make it into a machine much more easily. So you remember when we went from Roman numerals to Arabic numerals, people said, oh, Arabic numerals are so much easier to work with than Roman numerals. Well, you can make the transition from decimal Arabic numerals to binary Arabic numerals, and suddenly all of your arithmetic becomes easier. And that's important because then you can make a machine that does that. And so what we're doing here is we're seeing the way that we can work with numbers. We're coming up with number systems, and we're coming up with number systems that are going to actually be easier to turn into mechanical minds. Okay, and that's where I'm heading with this. All right, thank you for listening to my lecture, and bye-bye.